All right, so in this video, we're going to be talking about similar triangles. And the idea here with similar triangles is that if we know some information about one of the triangles, we know some information about the other one. And that is because the angles are all the same value and the ratios of the sides are going to also be the same value. So, for example, if I call this angle A, then I also know that this angle, if they're actually similar, has the same value of that top angle. Similarly, if I know this angle, then I know the value of this angle. These triangles are drawn to be right triangles just for simplicity, but this is true of any triangle, not just right triangles. And if these two are the same, then this one is also going to be the same. So in similar triangles, the angles match each other. And moreover, if I have values for these sides, then the ratios are going to be preserved from triangle to triangle. So to keep these to keep track of these, we're going to call these ones subscript 1. And then the other ones we'll call subscript 2. Oops, wrong side. X2, Y2, Z2. So what do we know? So we know that whatever the ratio is between, let's say, X1 and Z1 is going to have to be the same between X2 and Z2. We also know that any relationship between X and Y will also be preserved in the new triangle. We also, again, same thing for Y related to Z. All of these ratios are going to be consistent. And if we rearrange these, we can also get information about the ratios between the triangles. X1 over X2 is going to have the same ratio as Y1 over Y2. So this is the power of similar triangles. And so typically we use these for scenarios where we know something about one triangle and we're trying to determine something about the other triangle. All right, so let's look at some examples of working with similar triangles. Now, let's suppose that we have two triangles that we're told are similar. And on one triangle, we have sides given as 6, 9, and 12. And we have another triangle where we're given information about one of the sides being length 4. Now, what we are wanting to do now is to find the lengths of the other sides. Now, again, there's different ways that we can represent this information in this triangle. You will sometimes be told or given problems where the triangles are actually literally stacked on top of each other, like so. This is a way of sort of providing that information. These lines here are parallel. This angle is identical. That means that this angle and this angle are identical from other properties of geometry. But you can always take the two triangles apart and separate them so that you can think of them as completely different triangles and not working with them on top of each other. So if I have this information, then I have a bit of information about the ratio of these two sides. So I know that there is a relationship between these triangles in that these two shortest sides have a ratio of 6 to 4. Now, if I want to find this vertical side here that has a ratio of 9, I called this X in the previous example, the previous setup. So we'll call this x again. And now I just have to solve this ratio in order to find x. So I'm going to cross multiply. I'm going to get 6x is equal to 9 times 4 is 36. And so if I divide by 6, I get x is 6. And I can do exactly the same calculation again for this long side. We'll call it z. The 6/4 ratio is still there. But now I'm going to be relating this 12. Again, keep in mind which order you're putting these things in. That's important for ratios. The bigger triangle was on top here. So same thing over here, 12/z. And if I now do my cross multiplying, 6z is equal to 48. And then I divide by 6, z is equal to 8. And so now I have all the sides of my smaller triangle because I know they have a common ratio with this larger triangle. Again, the relationship matters that one of these ratios is complete and the other ratio is partially complete. So as long as you have 3 pieces, you can put together a ratio. If you're putting things in the same place in your ratio that correspond to similar things, then there are different ways of setting this up precisely so that you will still get the same information. We could easily have set up a ratio 9/6 and then 4/x in the first equation. 9/6 equals x/4 would also have been a perfectly good setup for solving this problem. And you can see that if you actually solve it, you get exactly this equation, 6x equals 36, because the elements are in the same, they're in the corresponding parts of the equation. So don't get hung up on which is the perfect ratio to make. As long as you have one complete ratio and one partial ratio, then you'll be able to solve for the missing piece.